So last time we talked about partial derivatives, which is a method of finding the slope on a graph at a certain point in a certain direction. And we were thinking of it as a motivating idea to what the derivative was supposed to be in two variables. So now let's ask this question. What does it mean for a function to be differentiable at a point in 2D? Well, remember in Calc 1, the definition we used was f of x is differentiable at x naught if the derivative f prime at x naught exists. So it seems reasonable that the definition we should take for a function of two variables who has two derivatives to work with, del f, del x, del f, del y, is that they should exist. I mean, what could be more obvious? Unfortunately for us, this is the wrong definition in two variables. To show you why it's the wrong definition in two variables, let's start off with a simpler problem, the problem of finding a tangent plane to a surface at a specific point. So to start us off here, let's imagine that we have a function of two variables whose graph is suspended over the xy plane. Let's say we've got a specific point right here, x naught, y naught, and its corresponding point up here on the graph. Now we know what this point is, because, well, it's on the surface z equals f of xy. So if I know the x value and the y value, then the z value has to be f of that. So we're looking at the point x naught, y naught, f of x naught, y naught. Now, we would like to see if we can find the equation of the plane who is tangent to this surface through this point. So a plane who just skims the surface of this graph, but passes through the point x naught, y naught, f of x naught, y naught. How could we find the equation of a plane like this? Well, we know that the equation of this plane, whatever it is, it has to take the form of n dot the variable x vector equals n dot a point on the plane expressed as a vector, where n is the normal vector to the plane, and p is a point on the plane. Well, we happen to know a point on the plane, so if I write it in vector form, it's the point x naught, y naught, f of x naught, y naught. And x is simply the vector x, y, z. So all I'd need to get this job done is to figure out the normal vector to the surface. Well, if we could find two vectors who were tangent to the plane, then their cross product would be the normal vector. Could we find two vectors who are tangent to the plane right here? Well, you might remember we did an example yesterday of finding the equation of a tangent line to a plane through a point. Such a line would have to be tangent to the surface and therefore would belong to the plane. So it would give us a parallel vector. If we found a tangent line in the y direction, same argument. So let's review what we did last time. Let's say we wanted to go and find the slope in the x direction at this point. So the slope in the x direction would be the partial derivative of f with respect to x, evaluated at the point x naught, y naught. So what that would say is that the line tangent to the surface at this point would go for every 1 unit, and I'm going really out of scale right here, for every 1 unit in the positive x direction, it would rise or fall this amount, del f del x over x naught, y naught units, because that's the slope in the x direction. So, put that together, what we found is we've got a vector. I'll call it vector subscript x. A tangent vector in the x direction. This would be a vector who, for every 1 unit in the x direction, the z value would go up or down by the partial derivative in the x direction at f naught, y, or x naught, y naught. And I'm going to use the subscript notation for just a second. And since I'm only moving in the x direction, the y component would be 0. So here would be one tangent vector to the plane. We could do the same thing in the other direction. We know that the slope of the graph in the y direction at this point is going to be the partial derivative of f with respect to y at x naught, y naught. That means for every 1 unit we march in the y direction, the graph will rise or fall exactly del f del y at x naught, y naught units, because that's going to be the slope of my tangent line. So that means we'd have another vector who's tangent to this plane. Every time we increase 1 unit in the y value, the z value changes by f of y x naught, y naught. And the x value doesn't change at all since we're moving in the y direction. So now I have two vectors tangent to the plane. The vector vy that we just found, and the vector vx we found a moment ago. Since these two vectors are tangent to the plane, their cross product will be orthogonal to it. And so we can find our normal vector by taking the cross product of vx and vy. So let's do that. We'll take I, j, k. Let's stick in this vector here, and let's stick this vector here. So then if we expand this out, that's going to get us the vector negative f of x at the point x naught y naught I minus f sub y at x naught y naught j plus k. And so now we have a normal vector, and we can take that normal vector and plug it into the two places where we were missing it from before. Like so. Now let's clean up our space and work out this dot product. We would get negative the partial derivative of f with respect to x at x naught y naught times x minus the derivative of with respect to y at x naught y naught times y plus z is equal to negative the derivative with respect to x at x naught y naught times x naught minus the derivative with respect to y at x naught y naught times y naught plus f of x naught y naught. Whoo-wee! So there's the equation of the tangent plane. Now, I'm going to make one slight change right here. I'm going to move these two pieces over to the side. So the left-hand side will just read z equals. When we move this piece over to the left-hand side, we're going to have f of x at x naught y naught times x minus fx x naught y naught times x naught, which is just the derivative of f at x naught y naught times x minus x naught. Similarly, we're going to have f derivative of y at x naught y naught times y minus y naught. I've been leaving off this guy right here, who I'm simply going to move to the front. And I'll write this as f of x naught y naught. And so this formula right here is actually a little bit easier to memorize. It says that the equation of the plane tangent to the function f at the point f of x naught y naught is equal to z equals the z value times the x slope times the change in x plus the y slope times the change in y. And that's not too difficult an equation to work with. Of course, we did this purely symbolically. It might help to see it on an example. Let's go and pull out our favorite function in surface, the paraboloid z equals x squared plus y squared. And let's see if we can find its tangent right here at the point 1, 3. So our formula is that the tangent plane is given by z is equal to the z value plus the x slope times delta x plus the y slope times delta y. It's a nice way of sort of encapsulating that. So it's going to equal f at the point 1, 3 plus the derivative of f with respect to x at 1, 3 times the change in x, which is x minus 1, plus the derivative in the direction y at the point 1, 3 times the change in the y values, y minus y naught. So let's work out those individual values. F of 1, 3 is going to be 1 squared plus 3 squared, which is 10. What about the partial derivative of f with respect to x at the point 1, 3? Well, we need a dogleg to figure out what this is. So if we were to take the derivative with respect to x of x squared plus y squared, we're going to get 2x. If we evaluate this at the point 1, 3, we're going to get 2 times 1, or 2. Similarly, if we take the function x squared plus y squared and we differentiate it with respect to y, we're going to get 2y. If we plug in the point 1, 3 into 2y, we're going to get 2 times 3, which is 6. And so our equation should be z is equal to 10 plus 2 times x minus 1 plus 6 times y minus 3. If we clean that up a bit, we're going to have z is equal to 10 plus 2x minus 2 plus 6y minus 18, or z is equal to 2x plus 6y plus 10 minus 20, or minus 10. And so there's the equation of our tangent plane. Of course, this is just done entirely symbolically. Let's go and have Maple take a look at this surface and this plane and see if in fact they look like they're tangent. Here's the surface, which is that paraboloid we were talking about. Now let's go and put the plane on it. And so here it is, and if I take a look at this, it certainly looks like it's just coming by and just glancing the surface at one specific point. Now there's a nice view of it right there. It just sort of disappears on the razor's edge. But it certainly looks as though this plane is tangent to the surface. Let's try a slightly less trivial example. Let's find the equation of the tangent plane to the function f of xy equals x times the cosine of pi xy squared at the point xy equals 2, 1. Now the equation of the tangent plane is z equals the z value, f of 2, 1, plus the slope in the x direction, del f del x of 2, 1, times the change in the x values, x minus x naught, plus the slope in the y direction, at the point 2, 1, times the change in the y values, y minus y naught. So now we just need to work out these individual values. F of 1, 2 is easy enough to work out. We know that f of xy is equal to x times the cosine of pi times x times y squared. And so f of 2, 1 will be 2 times the cosine of pi times 2 times 1 squared. Cosine of 2 pi is 1, and so that's going to get us a grand total of 2 for this first term. To work out the derivative with respect to x at the point 2, 1, let's just first find the derivative with respect to x. So if we differentiate this expression with respect to x, we can use the product rule. It's the derivative of the first times the second, plus the first term x times the derivative of the second. The derivative of cosine of blank is negative sine of blank times the derivative of blank. The blank is pi xy squared. Since pi and y squared are constants, they'll come along for the ride, and the derivative of x is 1. So this gives me a grand total of the cosine of pi xy squared minus pi times x times y squared times the sine of pi xy squared. So there's my derivative at every point. So if we take the derivative only at the point 2, 1, then this will become the cosine of pi times 2 times 1 squared minus pi times 2 times 1 squared times the sine of pi times 2 times 1 squared. The cosine of 2 pi we've seen was 1. The sine of 2 pi is 0. And so that's going to give us a grand total of 1 for this entry right here. Lastly, let's focus on this derivative right here, which is actually much easier. If we take the derivative of f with respect to y, well, the function is right here. The x is a constant, so it's going to come along for the ride. The derivative of cosine blank is negative sine of blank times the derivative of blank. The blank in this case is pi xy squared. Pi x is a constant, comes along for the ride. The derivative of y squared is 2y. And so that will become negative 2 pi x squared y times the sine of pi xy squared. If we plug in the point 2, 1, then we're going to get 2 times pi times 2 squared times 1 times the sine of pi times 2 times 1 squared. But since sine of 2 pi is 0, this whole term vanishes. And so now that we know what the three numbers are, 2, 1, 0, we can write the equation. Z is equal to 2 plus 1 times x minus 2 plus 0 times y minus 1. So z is equal to 2 plus x minus 2, or z is equal to x. So there's the equation of our tangent plane. Is it tangent to this function? You're not going to see me plotting this one by hand. I'm going to fire at Maple. So if we were to go and have Maple plot this surface, we're going to suddenly realize just how happy we are that we didn't have to do this by ourselves here. This is what the graph of x times cosine pi xy squared looks like. A view from the top down shows just how complicated its level sets would have been if we tried to plot those. So what does this tangent plane look like? Well, let's stick it on here and see what it does. Whoa. Does that look like it's tangent to the surface? Well, you know, I might just call that as a yes right here. It certainly looks like it's scraping right down the flank of this one spot right here. But maybe the better thing to do is to see whether or not it looks like this up close. I actually plotted this on a fairly large graphing window. I have my x values going from -3 to 3, my y values going from -3 to 3. I wanted the tangent plane only at the point 2, 1, so let me graph it on a much smaller window. I'm going to redraw this picture, but I will zoom in on a smaller portion, and we'll obtain the following picture. If we take a look at this picture, now the point that we care about is right in the middle of it, the point 1, 2, 2, and it's pretty clear as day that we found a plane that's running right tangent to the surface right at this one point. So let's go back to the whole point of this discussion. We were trying to figure out why this was a bad definition. F of x, y is differentiable at a point x naught, y naught if partial f partial x at x naught, y naught and partial f partial y at x naught, y naught exist. That's what we did in Calc 1. Once we had a derivative, we had tangent lines. And we see here that once we have partial derivatives, we have tangent planes. So what's the deal? Why is this condition the wrong one? I just want to do one more tangent line problem for you, but this one's a little bit more technical than the other ones. Find the equation of the tangent plane to the function f of xy equals 2xy over x squared plus y squared at the point 0, 0. Now before we do any work, you should immediately cry foul, because look, I can't plug 0, 0 into this thing. I'll get a division by 0. So I'm going to make one slight modification. F of xy will equal 2xy over x squared plus y squared if we're not at the point 0, 0. But if we're at the point 0, 0, I'm just going to set the function to be 0. So we're going to make a piecewise function. Oops, if you're not 0, 0. Let's find the equation of the tangent plane to this particular function. The formula is going to be z is equal to f of 0, 0 plus the derivative of f with respect to x at 0, 0 times x minus x naught, which is 0, plus the derivative of f with respect to y at 0, 0 times y minus y naught, which is 0. What's f of x naught? Well, my function says if you plug in 0, 0 into the function, you're supposed to get 0. So f of x naught is going to be 0. What about this part? Remember, this is the slope of the function in the x direction at the point 0, 0. Now, because it's a piecewise function, you might remember from Calc 1 that we have to be really careful about taking limits of piecewise functions. So I'm going to do this nice and slow. Let me go back and calculate this the way we said to do it yesterday. The way we said to do it yesterday was to take the function. Since I'm differentiating with respect to x, I'm holding the y value fixed. So I'll look at the function f of x0, and then I will differentiate this function with respect to x. And then I'll plug in the point x equals 0. This will be a function of one variable, the variable x. I will differentiate this function and set x equal to 0. So what happens if you plug in x equals 0 into this formula? Well, if you plug x equals 0 to the formula here, you're going to get 2 times 0 times y over 0y squared. So the bottom is positive, the numerator is 0, you're going to get 0 no matter what you plug in. So I need to take the derivative of the function 0 at the point x naught. But that's just going to get me 0. So I now know that the slope in the x direction of this function is 0. So my tangent plane is now looking like z equals 0 plus 0 times x minus 0. What about this piece right here? Well, let's do it the same slow way. Whenever I have a piecewise function, I have to be really careful about taking derivatives. So I'm just going to follow the rules we set up yesterday. This is supposed to be the derivative of the function in the y direction at the point x, 0. X equals 0, y equals 0. So I'm going to start by fixing x to be 0 and just let the y values change. This gets me a function of just y alone. Then we'll differentiate this function with respect to y, and we'll plug in y equals 0. So what happens if you take this function and you plug in y equals 0? Well, the numerator will be 2 times x times 0. The denominator will be x squared times 0. So the denominator is positive, it's x squared. The numerator is 0. I'm getting 0 again. That just means I'm taking the derivative of the function 0. But its derivative is 0. And so I find that this piece is also 0. So what have we found out? we found out that the equation of the tangent plane is z equals 0 plus 0 plus 0. Z equals 0 is this tangent plane. Let's go and take a quick plot of this. So here's the graph of the function 2xy over x squared plus y squared. You might remember it from a couple of lectures ago when we were talking about limits of multivariable functions, because this was an important limit example right here. So here's the function. We worked out that its tangent plane was the plane z equals 0. So let me go and include that in this picture. There you go. Now, there are many things that we could say about this particular plane right here, but that it's tangent to the surface ain't one of them. It looks like it cuts the surface right in half as opposed to just grazing it. So what on earth went wrong right here? Well, the hint is what I said before. Do you remember what special property this function had when it came to limits? It was that it didn't have one. So what did we just see from this? If we have this function, f of xy equals 0 when x is at the origin, and 2xy over x squared plus y squared for any other point. If it has a tangent plane at the origin, it has to be the plane z equals 0. But that plane is not tangent to it. Why isn't it tangent to it? What's going wrong with this function? Well, remember, this function here is not continuous at the point 0, 0. Remember, we checked its limit 2 podcasts ago. We showed that if you took a directional approach along the line y equals x, then this function would become 2x times x over x squared plus x squared, which is 2x squared over 2x squared, or 1. So if we take the limit of this function as x tends to 0, we get a limiting value of 1. But that value is not f of 0, 0, because we set f of 0, 0 to be 0. Now you might go and say, well, isn't that easy to fix? Can't we just go and take what we did right up here? We'll cross off this 0, and we'll replace it with 1. But then if we do that, then we could approach along the x-axis. And when we approach along the x-axis, we saw that we got the limiting value was equal to 0. This function has no limit at the origin. Since it doesn't have a limit at the origin, it can't be continuous. And if you're not continuous, you can't be differentiable. Differentiability is supposed to be better than continuity. So whatever differentiability is supposed to be, just having partial derivatives, this condition right here, is not enough to get it for you. So what should we do for differentiability? Most of our applications in Calc 1 involved tangent lines. So maybe what we want to say is that a function is differentiable at a point if it's closely approximated by its tangent plane at that point. In other words, if you had a function of several variables, say this function right here, floating around in x, y, z space, what will it mean for this function to be differentiable? Well, we want it to sort of intuitively mean that it's sort of nice and smooth right here. But a nice way of saying that is to say that the graph has a well-defined tangent plane that just grazes the surface at that point. This would allow me to rule out surfaces like a cone. This point down at the very, very bottom is not a point of differentiability because the graph, even if it has a tangent plane right there, isn't really well approximated by it. No matter how close I zoom into this point, it's always going to look like a cone. However, if you were to pick any other point on this graph, my gut feeling would say that that's nice and smooth, and if I were to zoom in on it a little bit more, I'd see it sort of gently curving, and if I were to zoom on it even more, I'd start to see it looking more and more flat. So to have a good tangent plane, to be approximated by a tangent plane, is to say that you look an awful lot like it up close. So let me give a slightly better version of this statement. We say that f of x is differentiable at a point x naught, y naught, if it's locally linear at the point x naught, y naught. And all that means is that f of xy, which represents the graph of the curvy function, is well approximated by this expression. which is the equation of the tangent plane. So we're saying that f looks like its tangent plane in kind of more precise technical language right here. This expression right here is sometimes called the local linearization of f of x, y, because this approximation right here is only valid if the point xy is pretty close to x naught, y naught. It's an up close and personal sort of statement right here. There is one thing to take away from this, though, is that the only way for you to be differentiable is to have partial derivatives. But our example shows that just having partial derivatives by themselves is not enough. Verify that the function f of xy equals x times y cubed plus x squared is differentiable at the point minus 1, 3. So our definition of differentiability is the statement that f of xy is well approximated by its linearization, by its tangent plane at the point minus 1, 3. Now its tangent plane formula takes the form of f at the point times the derivative of f in the x direction at the point times x minus x naught, plus the derivative of f in the y direction at the point minus 1, 3, times y minus y naught. So we could work out what this tangent plane is really quickly right here. Well, let's see. F of minus 1, 3 is equal to minus 1 times 3 cubed plus minus 1 squared. That would be minus 27 plus 1, or minus 26. What about del f del x at the point 1, 3? Well, del f del x in general is y cubed plus 2x. So at this one point in specific, the point minus 1, 3, we're going to get 3 cubed plus 2 times minus 1. So that would be 27 minus 2, which would be 25. That would go right here. And finally, del f del y at the point 1, 3, well, del f del y in general is 3xy squared plus 0. So at the point minus 1, 3, in particular, we're going to get 3 times minus 1 times 3 squared, or negative 27. So that will go right here. So let's plug in these values and see what the approximation is that we're looking for. So f of x is approximately negative 26 plus 25 times x plus 1 minus 27 times y minus 3. If we clean that up, that's f of xy is approximately negative 26 plus 25x plus 25 minus 27y minus negative 81. And if we clean that up further, 81 plus 25 minus 26 would just be 80. So we need to see whether or not f of x is approximately the same as 25x minus 27y plus 80 for x values, xy values, who are really close to minus 1, 3. So what I'll do is I'll have Maple plot this function really close to this point, in a very small neighborhood around this point, and see whether or not they match up. So here's a plot of this function, which looks something like, I don't know, maybe a manta ray swimming through the ocean. I've plotted it on a big window just so we could get a large look at it. This is the window, and the y values go between positive 4 and negative 4. The x values go between positive 4 and negative 4. And the z values take up quite a stretch of real estate. This is clearly not to scale. If you wanted to see what this graph looks like to scale, that would be what we would look like. Not helpful. So let's go and put it back into its regular scale here. Now, I want to check that it's differentiable only at the point minus 1, 3. So when x is equal to minus 1, y is equal to 3, I'd like to zoom in on the graph right around here. So let's do that really quickly. And this is what we'd get if we zoomed in. So we'd see a surface who looks like this. So our point that we're looking at is right dead center right here. And it certainly seems as though this piece of surface is very planar up close. In fact, we can go and plot the tangent plane to compare it against it. And so here's the tangent plane. And as we look, we can see it just sort of crossing right through the surface, just glancing it. It's tangent in this direction as the surface curves sort of round like this, and it's tangent in this direction as the surface curves this way. We're looking at something shaped kind of like one of the saddles we plotted earlier right here. Now, if we were to zoom in even closer, we would see that these two surfaces would look even closer and closer to each other. But it certainly is suggestive that this function is differentiable. It is well approximated by its tangent plane, as long as we stay really, really close to this one point. Now this might have struck you as kind of cheating a little bit right here. We found the tangent plane, but my only way of gauging whether or not the function looked like the tangent plane was to graph it. How could you do this without graphing the thing? If you do graph it, how do you know that the graph doesn't have a mistake here? How approximate is approximate enough right here? Is there any way to test if you're differentiable without having to go through the graphing process? And it turns out that there is. We have the following important criterion for differentiability. If the partial derivative of f with respect to x and the partial derivative of f of x with respect to y are continuous at the point x naught, y naught, then f is guaranteed to be differentiable at that particular point. Notice what it doesn't say. It doesn't say that if the partial derivative of f with respect to x and the partial derivative of f with respect to y exist, then you're differentiable. Just because you have partial derivatives, it doesn't mean you have a tangent plane who looks like you. You can keep in the back of your mind this example, because it's important to us. The example of 2xy over x squared plus y squared, who we looked at earlier. There's a second non-theorem worth paying attention to. Non-theorem number 2. If the partial derivatives exist, but they're discontinuous partial derivatives at the point x naught, y naught, then f must not be differentiable. That's also a false statement. It turns out that you can be differentiable, but have your derivatives be discontinuous. If you're interested, you might try plotting the function f of xy equals x squared plus y squared times the sine of 1 over x squared plus y squared. This is a function who is differentiable at the origin, but its derivatives are actually pretty wild and crazy when you try to plot them. I could maybe try to summarize these two things for you. So suppose you have a differentiable function. Then it is true that if you're differentiable, then the partial derivatives del f del x and del f del y have to exist. Because we need those guys to make the formula for the tangent plane, and being differentiable means you look like your tangent plane. However, the back argument is false. Just because the derivatives exist, it doesn't mean you're differentiable. On the flip side, if the derivatives exist and they're continuous, then that's good enough to get you differentiability. You are guaranteed to have a derivative that way. But you can be differentiable and not have continuous partial derivatives. Sometimes this condition at the top, which is stronger than differentiability, is called being continuously differentiable. Or in some books, it's called being C1. And you'll sometimes catch me using that phrase right here. There's one last important implication that comes out of this picture right here. If you're a differentiable function, the way we've defined it now, in other words, you look like your tangent plane, then this function will be continuous. So one of the key properties from Calc 1 is at least being preserved right here. Let's go and revisit this example to verify that the function f of xy equals xy cubed plus x squared is differentiable at the point minus 1, 3. So rather than going and working out the tangent plane and seeing whether or not we match, let's go and actually use this other test. Let's take a look at its two partial derivatives, and we'll see if they're continuous at the point negative 1, 3. So the partial derivative of f with respect to x is going to be, well, the derivative of the first part will be y cubed. The derivative of the second part is 2x. On the other hand, the derivative with respect to y will be 3xy squared plus 0. Now if we take a look at each one of these, both of these formulas are products and sums of the functions x and y. And since x and y are planes, f of xy equals x and f of xy equals y are the graphs of planes, we know that these are continuous. And they're continuous for any values of x and y. So we've done something better than that. We've not only shown that this graph is differentiable at x and y, we've shown that it's differentiable at all values x, y. And that's a pretty cool thing to be able to do with our theorem. Let's try a variation on the previous problem. Where is the function f of xy equals the square root of x squared plus y squared differentiable? Well, we could take a look at its partial derivatives, del f, del x, and del f, del y. As long as those derivatives are continuous, we know you're differentiable. Whenever the derivatives are discontinuous, we'll have to take a little bit more care in making a decision. So let's go and take the derivatives of these things. The derivative of the function, well, let me first prep f. The function is x squared plus y squared to the 1/2 power. If we use the chain rule, the derivative of blank to the 1/2 power is 1/2 blank to the minus 1/2 power times the derivative of blank. The blank is x squared plus y squared. The derivative of x squared plus y squared with respect to x is 2x. So those will cancel, and we're going to get x times x squared plus y squared to the minus 1/2 power. If we do the same thing on the y side, notice that the roles of x and y are completely similar. So we should just get y times x squared plus y squared to the minus 1/2 power, although you can double check it longhand. So here are our two derivatives. Now, where are these derivatives continuous? Well, we know that x and y are continuous, and so that means that x squared plus y squared is going to be continuous since it's a product and squares of things. We also know that the function blank to the 1/2 power, if you'd like t to the 1/2 power, is continuous as long as t is greater than 0. It can't be negative because it's a square root. It can't be 0 because it's in a denominator. So that tells me that the x squared plus y squared to the minus 1/2 power is continuous as long as the expression inside is positive. And so that just means as long as xy isn't the origin. So that answers the first part. This function is differentiable for all x, y pairs who are not equal to 0, 0. But what about at 0, 0? Just because you're discontinuous doesn't mean you're not differentiable. But just take a look at our formulas here. If we tried to work out what the partial derivative was at 0, 0 in the x direction, we would have 0 times 0 squared plus 0 squared to the minus 1/2 power. That would be 0 divided by the square root of 0. But the minute we do a division by 0, we know that 0, 0 is not in the domain. In other words, the partial derivative of f with respect to x isn't even defined. And we know that to be differentiable, you at least have to have partial derivatives because you need the partial derivatives for the tangent plane. So that tells me that since I don't have a partial derivative, I don't have a derivative. So we can go one step further. And we can say that this function is not differentiable at the point xy equals 0, 0. Even though it is continuous there. Because, well, here's the function f. And x squared plus y squared is always non-negative, so the square root of it, by compositions, will be continuous. Let's at least double check that on a graph and see whether or not that makes sense. So here's the graph of this function, and it wasn't picked completely at random. It's precisely the cone I had mentioned earlier. And so we found out that it was differentiable at all points away from the origin, which seems like it makes sense. The cone is a nice smooth shape away from there. But at the origin itself, we come together at a sharp point, just like the absolute value of x. And so we would think that that point right there shouldn't be differentiable. And in fact, it's not. Use differentiability to approximate f of 4.1, 4.8 if f of x is the function the square root of x times x plus y. What now? In what way is this a differentiability problem? I mean, it seems like all we're trying to do is do a simple calculation. F of 4.1, 4.8 is the square root of 4.1 times 4.1 plus 4.8. And so that means we're trying to take the square root of 4.1 times, 8.9. Well, this is where the calculation falls apart. I'm not going to be able to do this work right here without the assistance of a calculator. However, I could get you a decent ballpark estimate, right? I mean, this is about the same thing as the square root of, well, that's about 4. That's about 9. This is the square root of 36, which is 6. So I know it's kind of in the ballpark of the square root of 6, but I can't really tell if it's much above it or below it. So how is differentiability supposed to help me out with this problem? Notice that this value right here is actually nothing more than f of 4, 5. So what we've done is we've taken f of 4.1, 4.8, and we've approximated it by f of 4, 5. We've approximated the value of a function by a value close by. And the minute you phrase it like that, differentiability makes sense, because differentiability says that you can approximate functions by tangent planes. So just kind of looking at what these things are right here, it looks like x is playing the role of 4.1, y is playing the role of 4.8, and it looks like x naught's playing the role of 4, and y naught's playing the role of 5. So if we plug this in here, we're going to get f of 4.1, 4.8 is approximately f of 4, 5 plus the partial derivative of f with respect to x, evaluated at the 0.45, times x minus x naught. That's 4.1 minus 4, plus the partial derivative of f with respect to y at the 0.45, times y minus y naught. That's 4.8 minus 5. So f of 4, 5 we've worked out to be 6. This value right here, 4.1 minus 4, that's just a tenth. And 4.8 minus 5, that's just negative 2/10. So if we work out these derivatives here and here, then we'll have an approximation. Well, not so fast. Remember, the formula in orange is only valid if the function is differentiable at the point in question. So that means we should check its differentiability first. The easiest way to check differentiability is to compute those partial derivatives and just test if they're continuous or not. So let's do that. We'll take the derivative of f with respect to x. So I'm going to take the partial derivative. Let's prep this function. This is x times x plus y to the 1/2 power. And so I want to differentiate that. That's going to involve the chain rule and the product rule. But if I just distribute inside those parentheses first, it's really x squared plus xy to the 1/2 power. So now we can take the derivative of that. The derivative of this, of blank to the 1/2 power, is 1/2 blank to the minus 1/2 power, times the derivative of the inside. The inside is x squared plus xy. The derivative of that with respect to x is 2x plus y. And so that's going to get me 1/2 2x plus y times x squared plus x times y to the minus 1/2 power. That's our partial derivative with respect to x. Is this continuous? Well, that's a constant. That's a plane. The inside is a polynomial, a product of planes. So it's continuous. And then we have a composition with the function x to the minus 1/2, which we've already said is continuous as long as the inside is greater than 0. Well, remember, we're plugging in the 0.45. So at the 0.45, the inside is going to be 16 plus 20, which is greater than 0. So check it off. This function is continuous at the 0.45. We haven't proved differentiability yet because we need to work out the other derivative. But let me go and actually just plug in 4,5 into it right now, because that would tell me what this missing number is. At the 0.45, we're going to have 13/12. And so that's this value right here. Now, we just need to work out the partial derivative with respect to y and show that it's continuous at the 0.45. So first we'll take the partial derivative of this expression, and remember that once we prepped it, it was x squared plus xy to the minus 1/2 power. So the derivative of, not minus 1/2 power, positive 1/2 power, because the derivative of blank to the 1/2 will get me minus 1/2 blank to the minus 1/2 times the derivative of the inside. The inside is x squared plus xy. The derivative of this with respect to y is just x. And so we get 1/2 x times x squared plus xy to the minus 1/2 power. Just like before, this expression is a plane, so it's continuous. This expression is a polynomial, so it's continuous. And we've composed it with the function t to the minus 1/2 power, which is continuous as long as you stay away from 0 or negative numbers. And if we plug in our point in question, the 0.45, we're going to get 1/2 of 4 times the inside is 36 to the minus 1/2 power. And since the inside's not 0, we know 1, it's continuous, and 2, its value is a third. And so that's the missing value we need right here. And so now we have an approximation. F of 4.1, 4.8 is approximately 6 plus 13/12 times 10 plus 1/3 times negative 2/10. So if we were to clean this out, that's approximately 6 plus 13 1/20 plus minus 2/30. Now if we were to put those on the common denominator, the denominator would be 120. 6 becomes 720 1/20. 13 is already on the common denominator. And putting 30 on the denominator would be to multiply top and bottom by 4. And so we would have 720 plus 13 minus 8, or 725 1/20, which can be reduced, if we divide top and bottom by 5, by 145 24ths. So we get f of 4.1, 4.8 is approximately 145 24ths. Now if you wanted to sit around and do the long division on this one, and it's not terribly hard to go and do that, then what we would come up with is that this is approximately 6.0416 repeating. For comparison purposes, the actual value as computed by a calculator or Maple is 6.04069 and change. And so that's pretty good decimal place accuracy for adding up 3 fractions. The problem we just looked at is what's called a linear approximation problem. If it felt an awful lot like one of those Taylor series problems from Calc 2, you're not mistaken. It's very much the same idea right here. The basic idea is that we use the definition of differentiability to be able to approximate a complicated value of f if it's close enough to a familiar value of f for us. So I'm writing once again just the equation of the tangent line, or if you'd like, the equation of the linear approximation. If we were to move this piece over to the left-hand side of the equation, we could just write this as f of xy minus f of x naught y naught is approximately equal to del f del x at the point x naught y naught times x minus x naught plus del f del y at the point x naught y naught times y minus y naught. When it's written like this formula is sometimes written as the change in f is approximately del f del x times the change in x plus del f del y times the change in y. And so this formula is sometimes called the linear approximation formula. It allows me to detect small changes in the f value, the output, as long as I've got small changes in the x and y that I could work with. Of course, it only works provided f is differentiable. So whenever you want to use a linear approximation, always make sure you check if f is differentiable. And the easiest way for us to do that is to go and to make sure that its partial derivatives are continuous at the point in question.